Hello friends, hope you're having a fantastic day today. So now we are going to do a full course on everything there is to know about queue data structure. It is one of the fundamental data structures and also it has a lot of massive applications both in the real world and also it is very popular in technical interviews. So we will understand that what is queue, how it is being used, what are the different operations it supports, how you can implement queues, and then we will see that all the different popular, most asked and most important lead code problems that has been asked in tons of technical interviews. Queues goes well with lot of other data structures such as trees and graphs and arrays and stuff like that. So we will understand it from that perspective as well. So without any delay, let's get started. Now let's try to understand that how does queue work. Queue is a very simple linear data structure and we have all seen queues in real life in action. Basically, let's say that if there is a bank teller who is providing their services and bunch of different people wants to access these services. Typically, they are going to form a set of queue and this queue is going to follow the principle of simply first in first out. What is first in first out means that whoever was the first person within the queue is going to be the first person eligible to receive whatever the services that they are looking forward, and once they get done with their services, next person in line would come in and again do the same thing. So if more people wants to enter the queue, they are typically going to enter the queue in the back side of the queue. Meanwhile, the queue is going to keep on ending from the front of the queue. This is a slightly different data structure compared to the stack that we have seen before, where stack typically operates in last in first out principle. Meanwhile, queue operates in the first in first out principle. And there is a difference on the stack. Both input and output typically operates at the same end. Meanwhile, the other end is always going to be sealed where nothing can happen. But in the queue, where we are going to have two ends typically, where one end is the place where new entries would be entering within the queue, and one end would be the place where all the previously existed entries are going to come out in the FIFO fashion. So think of it like a printer job in any particular company where there are hundreds of employees and a single printer. So printer is going to print whoever requested first and then they would complete their job and move on to the next candidate. So let's try to understand that what are all the different operations you can perform on any given queue. Now, I already told you that queue typically operates on two different ends, where we have one end where the stuff enters and one end where the stuff gets out. So let's try to understand that what are the different operations we can typically perform. First operation is enqueue. Enqueue means that we are inserting an element at the rear end of a queue. So this is going to be the first place where element gets entered, and if any new elements comes in, depending on the implementation, essentially this element would move forward in the place. So this is going to be X, and let's say a new element Y comes in, then Y would be typically entering once again at the rear end of the queue. Now same way we can enqueue, we can also dequeue. So dequeue means that we are getting rid of the elements that are already present. So eventually, let's say that this queue contains abcxy and they came in as the sequence of abcxy. So a would be the first element to get dequeued if we do this operation, and once doing that, essentially all of this cell is going to become empty, and all of these other previous cell would shift one place, and then they would be part of the same queue, where B would be the next candidate if we have to dequeue within the B. Now, there is one more operation we can do, and that is called peek, or sometimes it is also called front. So this simply shows that whatever the value is currently present at the very beginning of the queue. So in this case, if we do peek operation, we would fetch the value as B. If we do now same way, there can be another operation called rear. So rear simply returns that what was the last element that was added within the queue without removing it. And again, this depends on the implementation, but we can have a functionality where we can in some cases check for this results. Once again, in the queue we can also do is empty method. So this defines that whether the given queue is empty or not, and same way we can do is full method as well. So this defines that whether the given queue is full or not. So both can be done with any given queues. Now let's try to understand the common queue implementations. So most common way to implement a queue is using an array. Now we all know that how does an array looks like. It is typically a fixed size queue that is going to have one end where we enter the stuff or where we enqueue the stuff, and there is going to be a second end where we can dequeue the stuff. So in this case, there are some benefits and there are some discontinuations as well, because if we add stuff at the rear end, if we have one more value we are going to add, we will have to essentially readjust our existing array, and then we are going to have values like this. So if we keep on doing that for a bunch of different insert and delete operations, then in that case our whole system can basically operate for insert in the worst case in big of one value, or in the first iteration, initial iterations, the array might remain empty. So because of the fixed size there can be some concerns, but this is a common way to implement a queue. Same way, a better way to implement a queue is a linked list, where we don't have to worry about the size being fixed or not, because it grows and shrinks dynamically. So we don't have to care about that. On top of it, we always know that we are going to have our head that is going to point towards the first end or the first pointer that is currently present within the queue, and we are also going to have a pointer that is going to locate to the rear end of the queue. So if we have a new element we want to add, we can simply add it at the rear end without worrying about much about anything else, and then we can just have it point to the null pointer and then mark it as the rear end or the last element within the queue. And if we have to enqueue stuff out, we can simply go over the head of the queue and check out whatever the first pointer it is, and then we can get rid of it and then have our head point to the new element. So enqueuing and dequeuing becomes much more efficient, essentially in big O of one time, and this is going to be a much quicker way because we are not worried about having a fixed size queue at any given moment. So there is better memory allocation and faster way of enqueuing and dequeuing stuff. So in the most of the real world application, we typically have something like a linked list that is always going to be implementing a queue. Now there is also one more conceptual queue, that is the circular queue. Essentially it's an array based implementation, in which case we are going to have rear and front being close to each other or next to each other, and then we can start filling stuff from the front, and we will keep on going on and on and on until we reach to the rear, and eventually the next element would be the front. And if we have to remove stuff, we will just simply remove the stuff from the front position, and then we will update the existing front position to the next position available. So that's where we are going to essentially enqueuing and dequeuing stuff. So we are going to see a problem that defines that how does a circular queue operates, but it will give us some idea. Now let's talk about a couple of special queues. First one comes to mind is called double-ended queue. So in simple terms, we also write it as DQ, but don't get it confused with the DQ operation that we do. Okay, so let's understand the concept. Double-ended queue means, as the name suggests, we do both the operations that are insert and also removal at the both ends of the queue. So in simple terms, we can insert from both the ends, and if we have to remove elements, we can also do it from both the ends. Now in a typical queue, we simply follow the FIFO principle, but in a DQ or double-ended queue, we can do it in both the places. Now we can be restrictive about some cases. If we want to restrict it based on the input, we can say that input all only comes through one end, but we can have output going from both the ends. That can be an option. Or if we want to become restrictive based off of output, we can say that output will only happen through one way, but input can happen through both the ways. So there are some variations around DQ or double-ended queue, but more or less we have this implementation, and we are going to see some examples of this. Now question comes that why do we even need a scenario like this? Well, this is actually quite useful in many of the typical LeetCode problems we are trying to solve, something like sliding window approach or generating different palindromes. Second one is a called priority queue. Now this priority queue can also refer to as heap sometimes. Now this is a very unique case because we use heap in all sorts of places. Heap is an implementation of queue where we always store either minimum value or maximum value on one end of the queue. So we can have a queue that contains bunch of different elements, but when we are adding those elements, let's say that this is going to be a min queue. So we first try to add element number 5 inside it. Now currently this queue is empty, so 5 is the minimum value that is possible. So we can have 5 sitting over here. Then we are trying to add another value 3, but now 3 is smaller than 5, so the very first element present within the queue has to be 3, and then the whole queue is going to be readjusted. Meanwhile, if we had just followed the simple FIFO principle, where then 5 would have been the first position in the queue and then 3 would have been sitting next to it. But since this is a minimum heap that we are trying to maintain, basically we would have 3 come in over here. So why this is being used? This can be helpful in all sorts of priority queue based cases where we have some weight associated with any kind of queue that we are trying to maintain. Now don't worry about this, this is a very important concept. So we have created an entirely separate course on priority queues and bunch of different examples of that. So we are going to be studying this in very much depth because it's also one of the most popular topics at companies like Google and Amazon. So we will keep that in mind. Okay, now we have understood the basic principle on what queue is. Let's try to go over some most popular LeetCode problems that would really solidify our knowledge on queue related data structure questions. So the LeetCode problem we are going to solve now is called implement queue using stacks. This one is a LeetCode easy problem and also a very popular and important problem because we are tackling the core principle of two different data structures in a simple problem. So let's understand that what do we need to do. Basically, we need to implement a queue data structure only using two stacks. That is the whole purpose. And now we are given the definition that what operations do we have to support. So first operation is push. Push means that let's say that this is our current queue and current queue is empty. Now we all know the concept of the queue, that we have stuff entering from one end and going out from the other end, where we are following the principle of first in first out. So let's say that we first push an element 3, so that 3 is going to present within the queue. Now we also push one more element within the queue, that is 5. So now we have two elements living in the queue, that is 3 and 5, and then we add one more element, that is let's say 1. So now we would have three elements living, that is going to be 3, 5 and 1. So now we have three elements within our queue. Now next operation we'll have to support is pop. So if we pop one element out, basically we would be popping 3 out, then we only have 5 and 1 present within the queue. Now next operation we need to support is peek. So peek means that we are not popping the element out, but we are checking that what is the first element that is eligible to get out or at the top of the queue. So in this case that element is going to become 5, so this would have returned 5. And last one is empty. So currently our queue contains two elements, 5 and 1, so this is not an empty queue. So in this case we would return false. Now the problem is stack only follows the last in first out principle. So let's say that if I have given one stack and if I'm trying to enter value number 5 over here, this 5 is going to reside over here. Then if I want to enter one more value 1 over here, this 1 is going to reside over here. Now if I try to pop elements out, and I'm going to be eliminating value number 1 first before eliminating value number 5. But in the actual real world, where if I'm trying to have a queue like structure, I should have eliminated 5. Now lucky for us, we are being told that we can use two stacks to basically mimic a queue. So how we are going to use two stacks? Basically we are going to have one stack that is dedicated only for input or insertion steps. So whenever we need to input any element, we are going to put in this stack. So let's just call it an in stack, where we are only adding the values. Same way we are going to have another stack dedicated simply where we have to pop elements out. So we can call this an out stack. And now using this, we can actually implement queue very easily and very efficiently. So let's understand that what are the operations we will have to support. First operation we need to support is push. Second one is pop. Next one is peep. And last one is empty. Okay, so currently I'm not too worried about is on empty operation because it is like a given fact, so we can check it anytime. I'm more concerned about these three operations. So now let's try to see that how would this work in this scenario. So let's say that our queue is currently empty. Now we need to enter element number 1 in the queue. So we were always going to insert things in the in queue. So now we have pushed element number 1. Next sequence is that we once again need to push element number 5. So we are going to push element number 5 over here. Now next sequence is that we need to push element number 7. So now we are going to push element number 7 over here. Now I want to do a pop operation. Now notice that we always do pop operations through our out stack, but our out stack is currently empty. So whenever we find that our out stack is empty, but there are still stuff available in our in stack. So we are going to pop all the elements and then we are going to dump them in the out stack. Let me explain. So if I pop all the elements right now, basically I'm going to have 7 sit over here, then 5 sit over here, and then 1 sit over here, and this whole stack is going to become empty. Now if I have more values that are going to be coming in that I have to serve, let's say that any particular entries such as 6 or 7 or 8 or whatever, so those are always going to reside 6, 7 and 8 over here. But the thing is, I'm always bringing stuff out from the out stack. So the order of the way stuff has been entered and being taken out is always going to remain as it is, because now if I have to do pop operations, so first I pop, then I'm going to pop element number 1 out. Now notice that 1 was the first element that was entered. Then if I have to pop, the 1 is no longer here, so I would have popped 5 out. Then if I have to pop, once again 5 is no longer here, then I would have and kick 7 out. And now notice that this stack becomes empty once again. And notice that 1, 5 and 7 is the same sequence of elements that we originally entered stuff in our in stack or in the similar sequence. So we basically followed the principles of queue or FIFO, but using two stacks. Now once again our stack became empty. So the moment our stack becomes empty, all we need to do is just dump all the data. So once again we are going to dump all the 6, 7 and 8, and once again the sequence would get reversed, because we are no longer worried about stuff. And now if we, let's say, have to do peep operation, once again we are always going to do peep operation from out stack as well. So out stack is going to be used for pop and peep operation, and in stack is going to be used for push operation. And if we follow this simple philosophy, we can actually achieve first in first out using the two stacks that basically operates on the LIFO principle. And for is empty stuff, it's very straightforward, that if both the stacks are empty, we can simply return that whether our given stack is empty or not. So it's quite straightforward, so I'm not even putting any effort. Now let's talk about different time and space complexity. Okay, so time complexity for the first operation, that is push operation. So push operation is always going to be big of one because we are simply dumping a value within an array. Now for the peak operation and also for the pop operation, in the general case it's going to be big of one, because once we have already dumped all the data in the inside the out stack, it's very easy to take data out. But the thing is, occasionally we will have to basically do the operation of dumping all of these data over here, and worst case this can become big O of n. So there is just no way getting around it, because that's what we are using. And for is empty, it's also going to be big O of 1, because it's not going to take us a lot of time to check whether the given stack is empty or not. So overall, this was the full explanation on how we can do it. The idea is to just maintain two stacks where one is always going to be used to input stuff and one is always going to be used to output stuff, and then we would be able to achieve this. Now let's see the coding solution. So the coding solution is quite straightforward. We have our class myQ, and we are going to be using couple of DQs or double-ended queues to implement our in stack and out stack. Now let's notice, and we will keep on going on each of the methods. So for the push method, it's quite straightforward. We are simply going to push inside our in stack. For same way for the pop method, first we are going to check that whether we need to move from the pop or not, and then we simply are going to pop it from our out stack that we have defined. Same way for the peak, once again we are going to be using the method move if needed. This is a helper method we have created that basically helps move all the elements from in stack to our out stack. And then this is also going to return that what has been the peak result from this out stack array. And for the last one, we are simply going to check that whether both the stacks are empty or not. So we check that whether in stack is empty and out stack is empty. If that is the case, we can simply return true or false. Now our move if needed method is quite straightforward. We are going to check that if the given out stack is empty, then while we have any elements present inside the in stack, we are going to dump all of them into our out stack. And then once again we are going to come back to the appropriate out stack that is going to do pop operation or peak operation that we will have to follow. So let's try to run this code, and seems like our solution is working as expected. Let's submit this code. And once again, our code runs beautifully, beats 100% of all the other solutions. And that is because this also runs in big O of one time constant time complexity. So everyone is basically achieved this solution. So now the solution is present in our GitHub repository and link is in the description. So feel free to check it out from there. Thank you. So the lead code problem we are going to solve now is called implement stack using queues. Now this one is also a lead code easy problem and pretty popular problem because we are using two fundamental data structures to basically implement each other. So this is going to be interesting. Now we all know that stack has the property of LIFO, last in first out. So whichever was the last element would be the first candidate to get out. And meanwhile queues have the property that is FIFO, that is first in first out. Now we need to implement stack using two queues. That's the only thing we need to do. And then we are given that what are the different operations we need to support. So we should be able to push an element in at the top of the stack. We should be able to pop an element. And when we pop the element, it has to be from the top of the stack as well. Top only shows that what is the current element, but we are just not popping it out. And then empty method just defines that whether the given stack is empty or not. Now notice that we are going to be using queue to basically implement that, and lucky for us we are given the option to implement it using two queues. So here I have provided two queues, and these are the operations we need to support. Now I'm not too much worried about empty operations, so let's just leave it on the side for now. Important ones are push and pop, and top is going to be very similar to pop. The only difference is we are not just popping the value out. Let's try to understand that how does push operation would work in a typical stack. If we had stack like this, and let's say the entry we want to push it 3, it would come over here, then 4 it would come over here, then 5 it would come over here. Now in this case, if we had just one queue, basically we would have 3, 4 and 5 sitting in this order. But if we had to take this one out, then we would have taken 3 out, but meanwhile we should have taken 5 out. Now notice that we are trying to implement this using a single ended queue, not a double ended queue, because if it was double ended queue we could have just inserted from both the ends and it would have been easy for us, and also exited from both the ends. But that is not the case. So let's see that how does our push operation works in such a manner that the element we enter is always going to end up at the beginning of the queue. So for that we are going to do like something tricky. We are going to have q1 and q2, and whenever a new element gets entered, it always gets entered into q2, second queue. And we are going to make sure that q2 always remains empty for now, and then only we are going to insert the element. And once we add value to the q2, then we are going to dump everything that is in the q1 and then dump it into q2, and then we are going to swap names. So let's try to understand why we are doing each of these three steps, and let's see each of the three steps in action. So first step is that let's say I have value the one that I'm trying to enter. So 1 is going to come in the q2. Now currently in the q1 I don't have anything, so I don't have to move anything to the q2. And now last step was to swap names. So we are going to swap names between q1 and q2. Now why are we swapping names? Because remember we defined that q2 always has to remain empty where we are going to enter stuff in, and then things can change, but basically q2 we are always trying to make it as an empty queue. Now let's say that one more element 2 is going to come in. Now this 2 is also going to end up inside the q2, in the rear of the q2. And next step is going to dump everything we had from q1 to q2. So now we would have also inserted value 1 over here, so this is going to become 2 and 1, and this current q1 is going to become empty. Now after this is done, once again we need to have a q2 that is always empty, so we are going to replace the names. So this is now going to become our q2, and this is now going to become our q1. Now let's say there is an element 3 that we are trying to enter. Once again 3 is going to enter over here, then we are going to dump both of this 2 and 1 sequentially from q1 to q2. So this is going to become like 3, 2 and 1, and then we are going to have the names being replaced. So q1 is going to become q2, and this is going to become q1, and this is going to become an empty queue. Now notice that what is the property we are maintaining in each of the queue. We have inserted values 1, 2 and 3 so far. Now if this was just a simple stack, we would have entered values such as 1, 2 and 3. So 3 should have been the first candidate to get out, then 2 and then 1. Now if we have to start popping values out, basically we would always pop it from queue 1, and we would be able to maintain the property that this is going to look a stack like data structure, where the value is going to come out as if it was coming out of a stack. So this is why we are basically doing for the push operation, we are doing that always enter into the queue 2, then move everything from queue 1 to queue 2, and then swap names. So this is basically the whole core idea about solving this problem. Now some might say this looks like a trick, some might say this looks like something that you mugged up. If you had just put down your pen and paper and try to do some permutations and combinations, eventually you would be able to come to this same conclusion as well. It's not very complicated. Now let's try to understand that how does pop operation work. So we are always going to be popping out from whatever the value is present from the queue 1 as if this was a normal queue. And for the top operation as well, we are just going to see that what is the current value at the top of the given queue 1, but we are just not going to remove it. And for the empty function, now notice that queue 2 is always going to remain empty, so we don't have to worry about it. For is empty method, we are going to check that whether the queue 1 is empty or not. If it is empty, we can return true, otherwise we can return false. And this is the whole solution basically. Now let's try to understand time and space complexity for each one of them. Now time complexity is going to be big O of n for all the insert operations, because we are flipping things around and changing names and whatnot. But for in order for top and for pop method, this is also going to be big O of 1, and for empty method, this is also going to be big O of 1. And for the space complexity, since we are already given two queues, we are always maintaining one queue to be empty. So basically we are utilizing n extra space. But the thing is, since this is already given, so I don't think we need to worry about that much. So now let's quickly see the coding solution for this problem. So the coding solution is quite straightforward. We are defining queue 1 and queue 2. These are the two queues we are going to be using, and we are using linked list to implement them. Then we are going to simply implement our push method. So for that, step 1 is to add elements to the queue 2. Then step 2 is moving everything from queue 1 to queue 2. So while queue 1 is not empty, we are going to enter everything into queue 2. And then last thing is, using a temporary queue, we are going to be swapping the names between queue 1 and queue 2. So now this is the main operation, push operation. So one that has been taken care of by the 3 steps we defined. And then for the pop, we are simply going to poll whatever the first element is present inside the queue 1. And for the top, we are just simply going to use peek method inside the queue 1. And for empty method, we are going to check that whether this given queue is empty or not. So let's try to run this code. It seems like our solution is working as expected. Let's submit this code. And our code runs fine, beats 100% of all the other solutions, which is pretty good. But since this is running in like a constant time, so that's why we are seeing this result. Once again, the coding solution is present in our GitHub repository, so feel free to check it out from there. Thank you. So the LeetCode problem we are going to solve now is called design circular queue. Basically, we need to implement a FIFO-like structure. Now we all know that what FIFO is. It is simply a queue where you enter stuff from one end and then the stuff gets out from the other end. So whoever was the first in the queue would be the first to get out of the queue. Now this is going to be a similar structure, but this is going to be a circular queue. So the last position inside the queue is also going to circle back to the first position inside the queue to make it a circle, and we can also refer to it as a ring buffer. So let's try to understand that what is the difference between a normal queue and a queue that is a circular queue. So this is currently a normal queue. Now inside the normal queue we can have, let's say this is going to be our front of the queue and this is going to be the rear of the queue. So let's say that we started entering stuff at the front of the queue. So then we can have entries like 10, 11, 12 and 13. Now let's say for some reason we get rid of this 10. So in this case, because even though we get rid of this 10, currently this space is empty, we always enter stuff in the queue at the rear end. So basically we cannot enter stuff over here unless we do the operation of moving all of these entries one by one, and then only we can enter stuff over here. So you can notice that how quickly this can become annoying, and we can have like basically insertion happening at either big O of n space, or basically we just choose not to do if we are using an array based implementation. Now let's try to understand that what is the concept of a circular queue. So we notice that we are going to have a queue that is once again going to look like this, but the position of front and rear is going to keep on shifting from every time we enter, and basically if we reach to the end, basically the rear is going to switch back like this. So even though it looks like a normal queue, visually we can understand it to be more of like a circle, and we can have like a circle like this where we can basically enter 4 values. And let's see that how this is going to work in action. Let's say that currently our front is also here and our rear also sits at the same position. Okay, and we are always going to enter stuff from the at the rear place, and we are going to eliminate stuff from the front place. So front we basically dq, and at the rear we basically nq. Okay, let's try to just understand this for now. So we are going to have our front and rear right now, and at the rear end we are going to enter stuff. So let's say that we want to enter value number 10 once again. So we entered value number 10, and let's try to see that how does it look inside the ring or ring buffer as well. Okay, now our front is going to remain over here because this is where we can get stuff out. You get out of from the queue from the front of the queue. Okay, not from the rear of the queue, but you enter through the rear of the queue. Now our rear is going to change, and this is going to be our new rear. So once again, let's say that value we are going to enter is 11. So we can enter 11 over here, and notice so far this is the front. Okay, so front is not changing, but rear is changing. And once again, let's say if we have to enter value number 12, once again the rear is here. So because we entered 12 over here, and this is where rear is. And if we have to enter value number 13, once again we would be able to enter value number 13 over here. Now this time rear sits over here, and same way for value number 13 the rear sits over here. Now notice that in this case, because we have front and rear constantly switching, now if we have to enqueue any more elements, we cannot do it. Why? Because the whole queue is full. So since this is already full, we cannot enter stuff right now. So what is going to be the next approach? Okay, let's say that we get rid of some elements. So we do like dq and then dq again. So we get rid of 2 elements, and notice that we are always removing from the front. So we got rid of this 10. So now this is no longer here, and our front switches back to the next element. So now this becomes our new front. And same way, if we get rid of 11 as well, once again our front switches again, and then we can get rid of this element as well. Now notice that if we have to enter stuff in, basically we are going to check that whether the queue is full or not. Queue is currently not full, so we can just simply switch our rear to the next element, and here we can enter value number 14, and our 14 is going to live over here. Meanwhile, if we have to remove element, we can still remove 12 because we already have it covered through the ring buffer. And notice that previously in the previous queue we had to basically like jump the elements. We don't have to do that. We are simply jumping the pointers, and we are utilizing the same space to basically work as a circular queue. So this is the whole concept. And if we go back to the problem statement, let's see that what are they asking us for us to solve. Basically, we want to implement a myCircularQueue class. Now for this class, we will have to implement these methods. So first method is called front. Front means that it only gets that what is the front element from the queue, and if the queue is empty, we return -1. Rear means that we only get the last element of the queue, and if it is empty, we return -1. But basically we are just fetching that what is the current value. We are not removing them from the queue. Next element is boolean nq, and it has value. So we are going to check that what is the value we have to insert, and if the insert is successful, we return true. If it is not successful, we return false. Same way for dq, if it is successful, we return true. If it is not successful, we do not return true. But dq means that we are kicking element out from the existing queue. And then we have two methods, is empty and is full. This is simply to check that whether the queue is empty or whether the queue is full or not. So once again, let's just repeat all of our operation. We all know that how does NQ and DQ is going to work. Same way front and rear can also work. Basically, we simply have to fetch that what is the current value at the front of the queue and rear of the queue. And then we have the method of is empty and is full. So how each of them is going to work, we'll just try to understand it visually very quickly. Essentially, we are doing the same operation. So currently, once again, we are going to have an array like this. Currently, both front and rear sits at the same place. And if we are being asked that what is the front and what is the rear, currently the queue is empty, so we can simply return empty. Now in this case, if we have to check that whether the queue is empty or not, all we can keep track of a counter called size, and that is going to initialized as 0. And then we can have a counter called capacity, and using this capacity, it would basically mean that what is the current capacity or how many elements it can hold in the queue. So current capacity is going to be 3. Now every time we NQ stuff, we are going to do size plus plus. Every time we DQ stuff, we are going to do size minus minus. So whenever we have to check that whether the given queue is empty, we simply check that whether if the size is equal to 0, then it is empty. If it is not 0, then essentially it's not empty. And for full, we only have to check that if the size is equal to 3 or whatever the capacity is. If size is equal to capacity, then it is full. If not, then it's not full. So these two are very easy to manage. We would be able to do it. For front and rear, it's pretty much the same concept, that we will have to have two pointers that are going to keep on switching between the given array to figure out that where we need to enter the stuff. Now a better way to do it is using the size variable, and I'll show it to you in the code that how we are actually going to be doing that. But for simplicity, we are just understanding that we will have two pointers, front and rear, that is going to be moving around the given queue. Now for NQ and DQ, essentially NQ we are entering some value as well, and for DQ we are just saying that whatever the value that just gets out, we don't have to return the value, we just have to say that whether it was true or false, that whether it kicked element out or not. So let's say if NQ is 10, so we enter value 10 over here, and then because we enter at the rear, then our rear gets updated to the next value in case we will have to NQ stuff. So currently now if we have 20, once again it's over here, our rear sits over here, front sits over here. Once again, if we have to NQ new entry, we will have to check that whether the space is available. If it is available, we enter to the next element by updating the rear pointer, and that's it. Now the queue is full because and once again, with everything we are increasing the size because all we have done is the NQ operation. So currently the size is going to be 3. And then if we have to DQ, all we have to do is just update the front counter and then get rid of this element from the given queue. And now our front sets over here. So once again, by manipulating front and rear pointers, we would be able to do all of these operations. I think it's more of like a conceptual problem than an actual implementation problem. So in my opinion, this should have been easy problem. It's just the only difference is we are playing around some pointers. And if we have to see time and space complexity for each of the operations, it's going to happen in big O of 1 time complexity because we are not doing anything special. In terms of space complexity, it would be big O of k, where k is the total size of the queue that we will have to be allocated. And now let's quickly see the coding solution for this one. Now let's try to understand the code. Basically, we have our myCircularQueue class, and we are going to have 4 different variables. First one is the data, that essentially the sequence will have to enter the data in. Then we have the capacity of the given queue, and then we have the head position. So this is going to be the starting pointer, and then we have the total size of the queue. So instead of just utilizing like front and rear both pointers, we are only going to be utilizing the position of size, so total size of the queue, and what is the current head position or the first position within the queue. And now let's try to understand that how our queue is going to operate. So essentially the constructor is going to return that what is the data is currently present that we have to enter, and then what is the given capacity of the given queue. So this is going to determine that how many elements we should be able to add, and head and size are by default going to be 0, so they are going to be starting at the first position. Now whenever we have the enqueue method, we are always going to enter it at the rear end, and whenever we have the dequeue method, we are always going to remove it from the front of the queue. So let's try to understand a couple of helper methods first. First one is empty and is full. So is empty method is quite straightforward. If the given size is equal to 0, we return is empty. If the size is equal to capacity, we return is full. Okay, now whenever we are enqueuing stuff, we will first check that whether the given queue is full or not. If it is full, then we can't do anything. If it is not full, then we are going to determine an element called tail that is going to give us the idea on where we have to insert the element, and that is defined by head position plus size modulo by the current capacity. So this is going to be our rear pointer where we are going to add stuff in, and then we can simply insert that value and then update the size of the queue. So first, let's repeat. First we will check that whether the queue has enough size to enter the value or not. If it does, then we are going to first of all find the rear pointer, and then we are going to add over there and then simply return true. Same way for the dequeue stuff, we are going to check that if the given queue is empty, then we can simply return false because there are no elements to be dequeued. If that is not the case, we will first try to identify that what is the position where we are going to be dequeuing stuff. So that is going to be head is equal to head plus 1 modulo by cap, and this is going to be our front pointer that we were discussing, and then we can reduce the size of the existing queue. Now, in terms of for the front and for the rear, it's quite straightforward. We simply return whatever the value is present at the head or at the tail of the given queue, and then we will again be checking that whether the given queue is empty or not. If it is empty, we can't return anything. If it is not empty, then only we will return. So this is a very simple implementation of all the 6 methods that we were discussing. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs beautifully, beats all the other solutions because it's more or less big O of one or constant time complexity. So once again, the coding solution is present in our GitHub repository. Feel free to go and check it out from there. Thank you. In this problem, we would be able to learn concepts such as queue, dynamic programming, breadth first search, a bunch of different graph concepts, and also how you can actually approach solving a problem from a very different perspective. So without any delay, let's get started. So the LeetCode problem we are going to solve now is called open the lock. And we can see that this one is a LeetCode medium problem, but we can also categorize this as a hard problem in some facets. So let's understand that what does the problem statement is asking us to do. We are given a lock that is in front of us that contains 4 circular wheels. Now we all have seen the lock where you can rotate it from 0 to 9, and we are currently given a lock that contains like 4 such wheels that we can control in different manner. Now we are given the starting position that is going to be 0 0 0 0, and we are also given a target value that represents the value of the wheel that we will need to reach in order to unlock the wheel. So that's pretty much quite straightforward. Now the thing is, we are also given a list of dead ends, which means we must avoid these dead ends, and no matter how we try to rotate around the wheels, we must always make sure that we never reach to a point where we are at a dead end. So we'll have to circle back around it or find some other way. And once we do that, once we reach to a target value, we need to return the minimum total number of turns that are required for us to make in order to reach to that value. If we can't reach, we will need to return -1. Now, the complicated part in this problem is actually understanding the whole problem. Now we are given an example of 0 0 0 0, which means 4 circular lock, but that makes things much more complicated. What approach I will do is, we will try to understand this problem on what if we only had just one lock, what if we had 2 locks or like 2 circle locks, and what if we had 3 circle locks, and then we will try to see that how we can form solution for a complex problem like this. So let's try to understand the problem. Let's say that we are currently given a target of 7, and we are given the initial starting position as 0. Now currently I'm not talking about dead ends, but I'll get back to it in just a second. So let's try to understand that from this 0 how can we reach to this 7. Well, first of all, from this 0 we have two options. We can either go from 0 to 1 or we can go from 0 to 9. Okay, now once again from this 1 we once again have two options. From 1 we can go back to 2 or we can go back to 0. But the thing is 0 we have already come from 0, so we are not going to go back to 0. Let's just say keep it for simplicity. From 9 we have once again two options. We can either go back to 8 or we can go back to 0. Once again we are not going to do that. From 2 we have once again two options. We can either go to 3 or 1. And from 8 we have two options. We can either go to 7 or we can go back to 9. So now we have reached to 7, and this is the solution that we are basically trying to achieve, the target value. So how many turns did it took us from reach to 0 to 7? Well, this was the first turn, this was the second turn, and this was the third turn. So 3 is the minimum number of turns required for us to reach to the value 7. Now let's presume that in this case, if we had a dead end located at position number 8, what would have happened in that case? Well, once again we would have proceeded in the same manner right now, but at the 9, the moment we saw that one option is 0, which we have already seen, and another option is 8, which is a dead end, so we cannot move forward with 8. So in that case this entire path closes for us, so we no longer would be able to consider this one. So the only way for us to move forward would be using this path, where eventually we would have reached to value number 7, and that would have taken us basically 7 different ways in order to reach that. And in this case 7 would be the minimum number of clicks we would have to make in order to reach to the final position. So that is the answer we will have to return. So now what are the things we are ignoring when we are building the solution? Number A, we are always checking that whether the solution we are reaching to or the data point we are reaching to, whether it is part of the dead end or not. If it is part of the dead end, we are simply stopping exploring any further from that point onwards. That's number one thing we are doing. Second thing is we are also checking that all the things that we have already seen, are we also repeating those or not, and we are not repeating those. So somehow we will have to find a way to keep track of that what are the different dead ends that we should never go, and what are all the elements that we have already seen that we should never go. These are the two intuitions we can build. Now let's try to explore a two lock system where we are starting from 0 0, and let's say for simplicity our target value is 19. So what we are going to do is that we have 4 different possibilities at this position. First position is going to be 0 1, next position is going to be 1 0, next position is going to be 0 9, and next position is going to be 9 0. So notice that for each character we are taking 2 possibilities on whether this value 0 can be the subsequent value 1 or the previous value 9, while we are keeping the other value unchanged, and then we are repeating the same process. So logically, even at the 0 1 location, once again we are going to have 4 possibilities. First possibility is that the 0 remains as it is. So in that case this 1 can become 2, so we can become 0 2, or we can, this 1 can also become 9, so we can become 0 9. Now notice that 0 9 is already here, but we are also once again we can compute beforehand. So eventually when we get to this point we might have already computed that, but let's not worry about that at the moment. So these are the 2 possibilities. What are the next 2 possibilities? So next possibility is that this 0 can be turned into 1, so it can either become 1 1 or it can also become 9 1. Okay, now let's try to calculate more possibilities, but for simplicity we are just going to consider the 0 9 because that is going to give us the answer. So the 0 9 can have one of the possibilities as 1 9 if we just convert this 0 into 9. So this is the target that we are trying to find. Now notice that how many clicks it took us. It took us 1 2 and then 3. So answer is going to be that it took us 3 attempts to come up with this answer. Now logically what we are doing to build this solution? Well, basically we are just building a decision tree for any given set of nodes. So what we are doing is we are currently given a starting point, so we can treat the starting point as one of the node within the graph that is going to be the entry point in the graph, and then we are going to have a connected graph where we, for each of the different possibilities, they are going to be the nodes in the graph, and each of the different connections we can make would be the edges within the graph. Now, once we find that from point A all the way up to point B we can reach in any particular fashion, then this is going to be, let's say, the answer that we are trying to get to. So all the different edges is going to be, sum of all the different edges is what we are looking for. So these are the number of clicks required for us to come to that solution. That's a given fact, right? Now, how do we get there? Basically, what we are doing is that at initial position, we have multiple different possibilities. For each of this possibility, we are exploring all the other possible options. Same thing we are doing for the previously calculated value, same thing we are doing for the previously calculated value, and so on and so forth. So logically, what we are doing is we are traversing in the level order or in the breadth of the given problem. So we are doing like what do we call as BFS, or breadth first search traversal, where from one point we are exploring all of its neighbors, and then for each of the neighbors once again we are exploring all of its neighbors, and some neighbors can be interconnected. That's where we are seeing an example where this 0 0 has a neighbor that is 0 9, which is also a neighbor of this 0 1, because once again it is connected. So logically we can say that this is connected to this point. So that's why this looks like a tree, but it is actually a graph, because there are circles or there are cycles that can be formed, and tree does not have any cycles. But let's not get into the different concepts. Let's just stay focused towards our actual problem we are trying to solve. Now we know that we are trying to compute a breadth first search. Now breadth first search is achieved using queues. So whenever you are trying to solve any particular problem and you reach to a conclusion that we are reaching a breadth first search approach, we will have to use a queue. How does breadth first search approach works? Let me give you a very simple example. Let's say that currently I have one possibility A. Now for this A, we are going to have three different neighbors. That is going to be B, C, and once again D. And let's say that for this B, once again I'm going to have all the many different like X, Y, and Z. These are going to be its neighbors. So what I'm going to do is, we know the concept of queue. It operates on first in first out principle. So we are going to insert A at the beginning of the queue. So currently my queue is going to be empty. I'm going to add a value entry A over here, and then I'm going to enter all the neighbors of A that are currently present. So these are the values going to be B, C, and D. And once I have explored all the neighbors of A, then I can get rid of A, because I have already processed A. But in the meantime, I haven't processed all the remaining values because they are still within the queue. So we will keep the queue going until we reach to a point where the queue is completely empty, and queue would only be empty if we have taken into the consideration of all the different neighbors that exist. So now for B, I have entered the value X, Y, and Z in the loop, and after entering that I can get rid of B because I have already explored this solution. And then all I need to do is just see all the neighbors of C. C does not have any children, D does not have any children, X, Y, and Z is what I was looking for. And let's say that Z is the answer that I'm looking forward to. I have already processed Z because through Q or through BFS, and then whatever the distance was from A to B to Z, I can keep a track of in some sort of, let's say, steps variable or answer variable that is going to be storing all the results. So this is the whole solution that we are trying to build. That now I gave you an example of one string and two string. Same can be true if we are given three different locks. Once again, we are going to have multiple different permutations and combinations that we can make, and then we would be able to just driving that solution forward. Now we know that we need to avoid dead ends and we need to avoid all the values that we have already seen. So what we would do is we would just create a hash set for both of these things. And after, because why are we creating hash sets? Because even though it's going to consume extra space, we will have a separate data structure that performs all of the search steps in big O of 1. So we are going to be storing the results that any pair that is part of dead end. If that is the case, we will just stop immediately and we would pop that element from the queue. So we would not be exploring any of the neighbors of that particular element. If we see that element is already, we have seen something, so we know for a fact that it does not lead to a proper conclusion, or its neighbors are already part of the queue, so we don't even need to consider that for our solution. and that would be able to give us eventually that we would reach to a node that is our target node based on just different probabilities or different permutations and combinations of solutions. Now, what is going to be the time complexity in this problem? So time complexity for this problem is actually going to be constant time complexity. Why? Because we are for sure given that there are only going to be 4 different possibilities. So since there are only 4 different possibilities within a log, the maximum number of combinations we can have is going to be 0 all the way up to 9999. So in total 10,000 combinations, and for each of the pair or each position we can have 8 possibilities. So it's 10,000 multiplied by 8. So overall we since we only have 80,000 possibilities, that is the maximum time, worst case time complexity we can have. So because this is a finite number, I'm considering this as a constant time complexity. But I know your interviewer is not going to ask you a number like this. What if this number pair was going to be in millions? So in that case, the time complexity would have been to go over all the different possibilities of nodes and edges within the given graph, and that would have been big O of m multiplied by n, where m is the total number of nodes and n is the total number of possibility for each of the nodes or total number of edges. So overall, your interviewer would be very pleased with this explanation of time complexity. For the space complexity, because we are using an additional hash set to store the values of all the already previously calculated result, it's going to be big O of k, where k is the total number of possible combinations we can add to dead ends and our hash set. So whichever is larger would be our space complexity. So I hope this solution makes sense. The core concept of this problem was to explain you that how does a BFS work and how you can break a complex problem down into bunch of different smaller subsets and then try to make your way around through building logic through that way. And now let's move on to the coding for this. So here is the coding solution. First of all, we are going to define a hash set that is going to take care of all the different dead ends that we are provided. And then we are going to check that if the dead end contains the 0, 0, 0, 0, basically the very first node, we can simply return -1. And also we can check that if the 0, 0, 0, 0 is the target that we are given, that is one of the edge cases, we can simply return 0 because we don't have to change any locks. Now let's see our breadth first search implementation. So we are going to have a queue where we will add bunch of things. We are going to have a hash set that where we are going to keep track of all the elements that we have already seen. And then we are going to start our queue with adding the value of 0, 0, 0, 0 as the first node in the queue, and we are also going to be marking it eligible for our scene hash set. So in future we don't just repeat the element. Now initially we are at step 0, so because we haven't made any clicks. Now our breadth first search implementation starts that until queue is not empty, we are going to check that what is the current size of the queue. Then we are going to check that for any single element that is currently present within the given queue, we are going to poll or get rid of that current item. Then we are going to check that whether that is present inside our one of our dead end. If that is the case, we will just get rid of it. We will just skip those states because we don't need to worry. We don't need to enter any of its subsequent neighbors. If that is not the case, if it is the target, then we can simply return the steps as well. If that is not the case, then we will have to generate all the neighbors by turning the wheel +or -1. And for each of those neighbors, this is the simple logic on how we are going to be doing that. For each of those neighbors, we are once again going to adding them up to the queue, and we are also going to check that whether they are part of the given dead end or the scene element that we have seen. If that is the case, we would not be adding it into the queue. If not, we would be adding it into the queue, and that goes for both turning it up and turning it down, both the different possibilities. And we will keep on repeating this, and with every new neighbor or new level being added, we will update our steps. So total step it takes to reach to that next possibility or set of levels. And if we have a combination, we should be able to reach it within this queue. If we don't, then we simply return -1. So this is the full coding solution. Let's try to run our solution. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs beautifully, beating almost 60% of all the other solutions, which is pretty good. We are also really efficient in terms of memory usage, so that is also nice. Now, once again, the coding solution is present in my GitHub repository, so feel free to go and check it out from there. Thank you. The LeetCode problem we are going to solve now is called data to Senate. This one is a medium problem, and also in this problem we are going to play a game between two political parties. First one is called Radiant and second one is called Dire. But for simplicity, throughout this video we are simply going to refer to them as Republicans and Democrats. If you want, you can read through this whole statement, or let me quickly explain you the rules. So the problem statement is, we are currently given bunch of different senators that are present in a simple queue, and each of them is going to be doing a vote. Now in this vote, each senator belongs to a different party. So we have some senators that are currently representing Democratic Party, and then there can be some other mix of a bunch of different Republican parties, but overall it's going to be either Democrat or Republican in whatever sequence. Now the thing is, we need to determine that which party is going to win. Now how would a party win? Basically, any single senator who comes in to vote, that senator currently has two abilities. Number one ability is that that senator would be able to kill someone's vote or get rid of some senator from the other party. So let's say that if this guy is a Republican, then this person can kill or get rid of a Democrat vote. So that Democrat would not be able to vote, and vice versa is also true. And second thing this senator can do is that if there does not exist any other person that they can eliminate, then this person should be able to declare victory. So let's try to understand that how this is going to work. And also the voting is going to keep on continue until there are existing senators present. So if one senator has done the voting, and if that senator survives, that senator basically moves to the back of the queue, and then voting would continue. So let's try to understand this with an example. Suppose we are currently given a sequence like this. This is a very small sequence. So what is going to happen? The first person currently in the list is a Republican person. So this Republican senator knows that there are more people currently present inside the given queue. That Republican senator also knows that they need to eliminate one Democrat, and that should be like the immediate first Democrat that they can find. Okay, so the first Democrat that they can find is going to be placed over here. So they are going to get rid of this Democrat, and what is going to happen is that then this Republican casted their vote and they cannot declare their victory because there are still more Democrats. So they are going to go to the back of the queue. So this is the initial position, RDD. Then after round one, basically we would have this guy eliminated. So we would have a Democrat and a Republican, because this Republican goes back and this Democrat comes to the front. And after round one, now once again it's Democrats' turn. So once again they know that there exists a Republican, so they will get rid of this Republican and then join the queue again. So in the round two, we would only have one Democrat left. And at this moment, we should be able to see that because it's only one Democrat, there is no one else to eliminate, then this guy is going to declare victory, and this is what we need to return. Now let's try to take one more slightly longer example. Okay, so let's say that we currently have 3 Republicans, then 4 Democrats, and then let's say we have one more Republican. Okay, so in this case, what is going to happen? Now logically it seems that the voting is divided fair and square, but let's see that how would things change with each different turn. So first turn is this Republican guy's turn. So he knows that this is a Republican, this is a Republican, he won't do anything, but this guy would get eliminated and then he would go back to the queue. So now we would have 2 Republicans, then 3 remaining Democrats, and then once again 2 different Republicans. After that, we will have one more Republican that would be able to kill or eliminate one more Republican. So basically we would have 1 Republican and then 2 Democrats, and then once again 3 different Republicans over here, because this guy would go back. once again this Republican would get rid of this Democrat. So and then they would jump to the back. So next round we would have one Democrat, and then we would have 4 different Republicans. After this one, this Democrat would get rid of one Republican. So now we would have this Democrat would go back, and then we would have these 3 Republicans and then one Democrat. And now this guy is going to get rid of this Republican, oh sorry, this Democrat, and in the end we are going to be left with 3 Republicans, and so they are going to be declaring the victory. So this is the whole solution or the whole problem statement. Now let's try to understand that how would we solve them. So at a very basic level, if we are only given, let's say, a simple scenario where we are given bunch of different possibilities, what is going to be the brute force approach that we can take? Well, it's quite straightforward. Number one thing we are going to do is, for each Republican or each R, we would have to keep on going into the remainder of entire queue until we find a D. If we find a D, we will basically eliminate this D, or somehow find a way that this D should not be counted based off of its index value, and then we would put this guy back. So then we would have a shorter string in the next round. So once again, now we are going to have R, and then D, 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 and once again this R, because this R goes back. And once again we are going to repeat the process. Now what is going to be the complication part? For each of the element, we would be scanning all the remaining elements, and we would be continuing doing that for all the different elements that are present. Now slowly we are reducing the size of our queue, but overall it's still n multiplied by n work we are doing. So this is going to be the worst case scenario, that this is how we would be able to solve this problem. Now let's see that is there a way we can make things faster in this existing scenario? Well, if this was straightforward voting, where we could just majority only wins, then we could have simplified in just one simple iteration. We would just go over this entire exercise and then try to find a place, whichever has the higher number of votes basically declares the wins. But this is not the case here, where if we let's take an example like this, that in this case we only have 2 Democrats and 3 Republicans. What's going to happen? This Democrat is going to eliminate this guy's vote and then would go back. So we would have D, and then RR, and then once again D. Then once again this Democrat is going to eliminate this guy's vote. So once again we are going to R, D, and D. So now this Republican can eliminate this guy's vote, but once again we would have D and R, and then this Democrat would be replacing this Republican's vote. So notice that even though we only had 2 votes over here out of 3 votes, still these guys win because of just sheer positioning. So a simple fall through would not work. What would be the approach or optimal way we can solve this problem? Well, we can solve this problem using 2 queues in this case. Now, how would we use 2 queues? Let me give you the whole solution. We'll try to walk through it. Let's take the example. Let's say that we currently have this kind of scenario, and let's see that who is going to win. Okay. Now we know that this what is their current positions in terms of location. We can mark them out. So let's just mark the index values, that where they are currently located. And at the same time, we are also going to keep track of them in 2 different queues, and each queue is going to represent one party. So we would have one queue that is simply going to represent the Republican Party, and then we are going to have another queue that is simply going to represent the Democratic Party. And for each of them we will have the positions of the queue located, and based on that we would decide that whether one should stay inside the queue and come back, or should they be eliminated. Now we know that queue follows the principles of FIFO, first in first out, and we are also going to be utilizing that in quite heavily. So let's start creating our queues. So, and we would be entering just the index positions in the queue. Okay, so currently we have Democrat and Democrat sitting at position 0 and 1, so 0, 1, and then this Democrat is sitting at position number 4. So let's just put it over here, and then we have 2, 3, and 5. So let's just put it over here. Now let's see that how our queue is going to work. First of all, we are going to be fetching both of these entries, and we would only pick the smaller entry. So we know that amongst 2 and 0, 0 is the smaller, which means 2 would be eliminated. So we would simply get rid of 2. So 2 would not be present anymore. But now with the 0, this 0 is going to the back of the queue. and what is going to be the back of the queue position. Basically, with every single size, the size of the queue shrinks by 1. So that's what we are going to put. So in this case, after this elimination, because we get rid of this Republican guy, now the position of this queue is queue becomes, instead of 6 we would have 5 elements, and this D is going to go to the very last element. So that element number is going to be 4, like index value is 4 and the position is going to be 5. So we would have 4 coming to the back of the queue. Okay, and at the same time this 0 would be eliminated from the existing queue. Now the same operation would get repeated amongst these two values. So amongst 3 and 1, once again 1 is smaller and 3 is larger. And notice that we are also keeping track of the current size of the queue. So this time the size is going to 4, the next time size is going to be 3. So the whoever gets added would be this entry would be added in our queue. So now amongst 3 and 1, because this 3 is larger, we can get rid of 3 because we don't care about it. And now this 1 is going to come back to the queue by becoming the value number 3. So let's rearrange these values, 4, 4 and 3. And then this guy is still 5. That is what the position is. Okay. Now, since we eliminated both of these guys, so notice that in the original queue, these two guys eliminated these two guys. So now we only have this D remaining, and they are trying to eliminate this R. And once again, this guy is going to eliminate. So comparing 4 to 5, once again, this is going to eliminate value number 5. So now this entire Republican queue is completely empty, and this the size of our queue is going to become 3 once again. So index position is going to be 2. So this guy would get eliminated and it would come back to the queue as value number 2. But now we don't have anything to compare against in the second queue, so we can simply declare this Democrat as victor, and this is the whole solution basically. Now I hope that the logic made sense to you, that how we were able to solve this problem. Let's try to talk about time complexity in this case. The time complexity is going to be big O of n, because we are simply iterating over this given queue once, and then we should be able to basically come up with the solution very quickly. So more or less it's not going to be like n square, it's definitely going to be smaller than that. In terms of space complexity, this is also going to be big O of n, or big O of because we are using two queues, that is going to be the size of all the number n present probably. So once again, this is the whole solution, and I hope it makes sense. Now let's see the coding approach for this one. And by the way, in this case, throughout this program, I refer to them as Republican and Democrat. There is no political implication. I'm just trying to explain it in simpler terms instead of using terms like radiant and dire. So yeah, this is what the problem was. So let's see the coding solution now. So the coding solution is quite straightforward. We are first of all going to define that what is the current length of our given Senate string, and then we are going to initialize two queues, one named R and the other one named D. For both the queues, we are going to iterate over the given string, and then we are going to keep putting the value in either R queue or the D queue that we have created. Now we are going to simulate different rounds, and our basic condition is quite straightforward, that until one of the queue is not empty, just keep on polling both the numbers from both the queues, and for each of the position, check that which queue is currently present that has the proper value, or that can eliminate the other value, and then either get rid of that value, and the remaining value would go back to the existing queue, and we would keep repeating this process. Now in the end, we are simply going to check that whichever the queue is not empty, basically we are going to declare that as the vector. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs beautifully, beating almost 73% of all the other solutions. It's also pretty good in terms of space complexity. And the solution is present in our GitHub repository, so feel free to go and check it out from there. Thank you.